So if you want to solve the conservation equations and the momentum balance, you have to solve for every single cell not only the momentum balance. Additionally, you have to solve the gradient with second order. So you also have to solve the diffusional effects. Maybe I have to explain this a bit. If the fluid flow comes from this direction into the cell, it will not always exit. All the amount of fluid will not exit at the other side totally. It can also happen that some of the fluid will exit at the side of the cells. So you will always have a flow in this direction and some convective flow also in the opposite side of the cell, but you will have additionally to this convective flow also diffusive flows, and they will exit the cell to the sides. So you don't even have to solve 3 equations, you have to solve much more, because you have to solve all the diffusive flows additionally. Okay, so I want to summarize the continuity equation. Here's a continuity equation. You have the duration of the density by the time. You have 2 convective terms of the equation, and additionally you have also diffusive parts. Yeah? So you can describe the change of density over time, and you can describe the net flow rate of mass according to the boundary. And because the mass balance will always have to be closed, this balance always have to be 0. So you must fulfill mass conservation for every cell. So why do you need this knowledge about mass conservation, about the conservation of the momentum flows? Please take a short look at our solver manager in CFX Solve. Yeah? Here we have the solver where you can monitor the convergence of your fluid flow, and if your simulation runs without any problem and it runs, nothing happens, you don't even have to open the solver manager. You can just let the simulation run and your result will be there. But what happens if there occurs a problem? Maybe you don't get convergence. Maybe your mesh is not a good quality mesh. Then you get a crash during your run. Then you have to open the solver monitor and you have to look if everything is okay. Yeah? If there's an error message, if you reach convergence, if you fulfill the mass balance. And to check all these things, you can have a look at this plot, and this red line here is the residual of the convergence of the mass balance. So if your mass balance in every cell is fulfilled, then it goes down. But what happens if your mass balance in a cell is not fulfilled? So if mass conservation is not reached, then this line will not go down, and you should not use the result, because then it's not a physical result, it's not the converged numerical result, and then you should take care. You can get a crash, of course, but you can also get a result that is not converged, and then you should not use the result. But even one thing that makes it a bit more difficult, even if convergence is reached, this must not prove that your result is physical. Yeah, please always take this into account. Okay, so And there's one symbol I want to mention here. I showed you the conservation equation, the mass balance equation, and I explained you that we need a derivation of these quantities of the squared variables in every direction. So in every three directions of our coordinate system. In a former lecture I showed you we don't have, we can have three-dimensional coordinate systems, but we can also have other kind of coordinate systems, maybe cylindrical or tetrahedral. And so for every coordinate system, for every mesh, the solution of your equations will be different, and also the formulation of your conservation equations could be different. But if you use this nabla, this gradient operator, this will always fulfill for every match. This is always mathematically right, the nabla operator. And so the nabla operator is really important for CFD because you can describe a gradient really fast. You only have one mathematical symbol to describe movement in every direction. And the nabla operator, yeah, where does it come from? Nabla, if you look at the symbol, it looked like a turnaround delta, and the name came from a music instrument, and they found it on a really old picture from antique music instrument, and the picture was found near the city of Ur. Today it's Iraq, Baghdad, and it's over 4,500 years old. And they took the name of this music instrument to name the mathematical symbol because it looks the same. And yeah, maybe mention this symbol is much older than the delta symbol, the Greek delta symbol. Okay, and maybe one additional thing, maybe you know the open source code OpenFOAM. It's an alternative code, open source code for CFD simulation, and the nabla company who owns the CFD code uses this nabla operator as a logo for their company. Okay, and here we have again a picture of this gradient. Yeah, you can also write gradient phi, or you can use this nabla, that's the same, or you can write it as a vector where you have derivations of phi in every direction. That's the meaning of nabla. So if you maybe, for example, write the momentum balance, and you have u, v, w variables, and you have to write a derivation of every variable in every direction, at least you will get 9 equations, and that's a lot to write. And if you use this nabla, you can write it much faster. So why is a gradient so important? What is a gradient? A gradient is a change of a variable from one amount to another. Maybe a gradient can be a velocity. If you have a change of your velocity from one velocity to the next velocity, you have an acceleration. So the acceleration can be the derivation of the velocity value. So if I try to explain it in this small sketch, yeah, I already mentioned the so-called isolines. Yeah? Here I show you some isolines, and we can have isolines of every variable. And that's also something you must take care. If you look at your results, please look at you can also make a plot of the isolines. Yeah? Isolines are always lines with constant values. If you have here on this phi1, you have a constant value of phi, and on phi2 you have a constant value of phi, and on phi3 you have a constant value. But if for example the value of phi3 is bigger than the value of phi2, you have a gradient between these two values. So if you make a derivation from phi1 to phi2, you have a change of the result. Okay. Okay, that's some important things. You have to know what is a coordinate system, what is an isoline, what means iso. Iso means the same. On an isoline you have always the same values. Okay, and of course gradient is something you should use in your argumentation when you present the results. Okay, here is another formulation of the divergence of a velocity vector. Yeah, the divergence or the gradient can also be formulated by derivation of one velocity by x, derivation of the velocity in another direction by y, plus derivation of the third velocity by the coordinate z. So this is a three-dimensional formulation. You can also define it two-dimensional or in more dimensions. Gradient can be used for all dimensions. Okay, then there's some operator I want to mention in CFD. Maybe you do not use it so often in other mathematical formulations, so maybe you do not know this operator. It's a so-called Laplace operator. And the Laplace operator is the square of the gradient. And you can use this Laplace operator really good to describe diffusion effects. Here we have again our derivation of phi after time, and we have our second derivation, and this is a movement, you can describe it in fluid flow with diffusion. Okay, and important can also be not only the movement of the fluid in the cell, so the gradient between two cells, you can also have rate of change inside every cell. For if you can imagine, you have, for example, gasoline, you can describe the movement of gasoline between the cells, but you can also have change of gasoline inside a cell if you have, for example, a combustion process. Then the fluid will disappear. Or you can have a source term inside the cell, then you will get more fluid inside the cell during the process. Okay, for example, here again, if you have a droplet of diesel and you have an amount of gas around this droplet and you have a combustion process, you will get a lot of gas inside the cell more. You will get, you have a gradient inside the cell and you have a source term inside the cell, and you must describe this rate of the source terms additionally. Okay. There again is a rate. The rate change for a stationary fluid element. You can have moving particles, you can have special positions, and additionally you can also have a rate change inside the cell. Okay, here again, that's the same, I just repeated a bit. Here's again our rate of increase of the fluid element. Here is a net flow rate, it's described ρ phi u, and we can have also a rate of increase. So be careful of the operators. Of course, if you have a rate of increase on the left side, you have a plus operator, and if you have a rate of increase of the fluid particle on the right side, you will get a negative operator. Okay. And okay. Here I try to summarize all the quantities a bit. We have a momentum in x direction, and we always use the symbol u for the momentum in x direction. And that's the same as in the CFX. If you work in the CFX, you see this coordinate system, you see the small coordinates, then you will mention the movement in x direction is always a u variable. Movement in y direction is always a v variable, and movement in z direction is always a w variable. And you need this knowledge if you have a look at the boundary conditions. For example, this pipe example. If you have an area if you have an opening or an entry in the area of the of the xy direction, then you need a velocity in z direction. So you must add the w velocity. Okay. And one thing I want to mention, I don't want to explain it too detailed. You can also refer to my lecture Fluid Dynamics if you're more interested in this topic. There's one quantity I must mention also in CFD because it's really important. I already mentioned the most important quantity is the density. Density is really important, and you have to enter the density before you start the simulation, because you have to tell the code if you use oil or gas or air or water, so you have to change the density to the right fluid. But there's another really important fluid property. It's nearly as important as the density, and this is the so-called kinematic viscosity. We use the symbol nu, the Greek symbol nu, and the unit is square meter by seconds. And we have also we must also enter the nu value before we start CFX, because we have to tell the computer if we have high viscosities or low viscosity. So what is a viscosity? If you can imagine, for example, honey. Honey is a really thick media. It flows in a different way than water because it has a really high viscosity. Water has a really low viscosity, so the fluid flow of water will be totally different if you compare it with honey. And all the oils, all the motor oils, they all have different viscosities. And there's one good example and YouTube video that explains you this oil viscosity. You can refer to the slides, you can look at the QR code or click on the link, and then you see this experiment where someone turns around our two vessels. There's a metal ball in every vessel, and he turns it around, and in the vessel with the fluid of the high viscosity, the metal ball will be a bit slower, and when you have lower velocity, lower viscosity, then the metal ball will flow a bit faster. Okay, and you need this viscosity to calculate the shear stresses. So the gradient multiplied by the kinematic viscosity will give you the shear stress in the center. So you have to, additionally to the momentum equations and to the mass balance and to the pressure correction, you have to calculate also the shear stresses inside the cell to get knowledge about the movement of the fluid. Yeah? And to calculate this, you have to multiply the gradient of the velocity with the viscosity, with the kinematic viscosity, and then you can calculate the shear stress. And you have to calculate shear stresses in every direction on every face of the cell. So again, additional equations we have to solve. Okay. And based on shear stress, based on pressures, we can also calculate forces. So also the net forces in every direction have to be calculated by the shear forces. Yeah? shear stresses. If you know the shear stress, if you know the area where the shear stresses act, you can calculate the forces. Okay, here again is a plot of the momentum equations, and maybe you can have a look on your own. Now we have again our dynamic term, our instationary term, we can have our convective term, we have our source terms I introduced, and additionally to these terms we must also add the derivations of the shear stresses in every direction. So you see it gets a really huge amount of equations, and sometimes in the code the derivation of the shear stresses are not really solved. Sometimes easier models are used where we don't have to solve all the shear stresses again. Okay, and now at the end of the slides I want to have a look at where we can see it again. Look in CFX, look at the convergence. We have the green, yellow and blue lines, and the green, yellow, blue lines describe the solution of our conservative equations of the momentum. So now you know, when you look in this diagram, you look for convergence, you know what it means. So here comes a conclusion, and that's it.